Okay, so we have been talking a lot this year about mass, and mass is an object's resistance to motion. It's considered the inertia of the object. It tells us how well that object is going to resist a change in its motion from where it's currently at. And that leads us to wondering, what about if we are not moving linearly, but instead we are rotating? Well, what we find is that our objects have a resistance to rotation. Now, that object's resistance to its rotation does include a dependence on its mass, but not just its mass, but also how that mass is oriented with respect to the axis of rotation. So if you think about a figure skater, as that figure skater is going very, very slow, and as they move their arms in or maybe compress their body closer to that axis they are spinning around, you find that they go faster. And you can obviously view dozens of those videos on YouTube. But what we find is that as we bring that mass closer and closer to that axis of rotation, we are going to see an increase in the speed, which means that we are having a decrease in that resistance. So what that tells us is that the moment of inertia of that body is less. Now, in general, if we look at the infinitesimal masses of an object, that moment of inertia is the sum of all of those infinitesimal masses times their infinitesimal radii out. So if we were looking at a point mass or a small child, it's just mr squared, where r is the distance out from the axis of the rotation. Now, obviously, we are not dealing with just only point masses. There are several shapes. Over the course of this year and next year, we will determine how these are formatted. But for right now, we're not going to do the calculus of it. I'm going to show you just some basic examples here. So we have some set objects where we are given their moment of inertia. So a thin rod, we have two options here. We have one about the center and one about the end. We have a hoop, if it's rotating about the center through the hoop, or if it's rotating like you would spin a coin. A solid sphere, and a hollow sphere or a spherical shell. Those are the big ones. Also a disk. Two formulas I will not give you is a disk and a point mass or a small child, which is just mr squared. Keep those in mind. So now, this thin rod through the center and through the end, how do we get those different formulas? Well, one thing we could use is a theorem that's called the parallel axis theorem. That parallel axis theorem says that if we look at how we have shifted from the center of mass to an axis parallel to the original axis, but just shifted over a distance, we can arrive at our new formula. So if we take our slender rod, the moment of inertia for our thin rod is 1/12 ml squared. Well, if I move it out to the end, we have m, and we're shifting it out L over 2. So we're going to have L over 2 quantity squared. So we're going to have 1/12 ml squared plus 1/4 ml squared, common denominator, and we're going to get from this 4/12 ml squared, or 1/3 ml squared. So this parallel axis theorem is a very important one that is very useful whenever we are moving from the center of mass to an axis that is parallel, just a distance away. So how are we going to find the moment of inertia of a rod if it's rotated about an axis perpendicular to its length, going through its geometric center. So I have a thin rod. My axis is going through the geometric center, and we're spinning about that. So I have 1 meter on each side, right? So if I look at my moment of inertia formula, that is going to be 1/12 ml squared. So it's going to be 1/12. My mass is 6. My L is 2 meters long. We're squaring that. So we're going to get 2. Now our unit here is kind of weird. It's going to be kilograms meters squared. So that's how we're going to get our moment of inertia from that. So what about if instead it's rotated about an axis parallel, but that axis is 0.25 meters from an end. So I now shifted over here. This distance is 0.25. So that means I have moved 0.75 meters. So my new equation, if I use the parallel axis theorem, is going to be that 2 plus md squared. So I have 2 plus 6 times 0.75 quantity squared. So that's going to give me 5.375 kilograms meters squared. But we don't just use it when we're looking at parallel axis theorems. Another trick we could do here is if I have a shape like a wagon wheel, I can create kind of a composite, if you will. So the first thing I know is that we have a rim. Okay, so that rim, if you will, it's a hoop or a ring. So that moment of inertia, we go back and we check our formula, mr squared. So we know we have a mass of 1.6. We have a radius of 0.3, and we're squaring that. If I look at the spokes of that wheel, I have 1, 2, 3, 4 rods that are all spinning about that center axis. So if I look at the rods, the moment of inertia, I've got 4 of them, and they're all going to be 1/12 ml squared. So I've got 4 rods that each have a moment of inertia. Their mass is 0.64 and their length is 0.6 meters, and we're going to square that. So to get the combined moment of inertia for the wheel, I'm going to find the moment of inertia for the hoop. So this I have 0.144 kilograms meters squared. The rod, I have 4 times 1/12 times 0.64 times 0.6 squared. So this is going to be 0.0768. And if I add those two together, I get the total moment of inertia is 0.2208 kilograms meters squared. So that's how we can find if we have a shape that's slightly unusual, doesn't match what we normally expect, we can go and break it down piece by piece. Now, if I have a shape like this, we have here an L-shaped shape. It has 3 balls that are connected with rods. First, we want to look at the moment of inertia if we're rotating about the x-axis. If I rotate about the x-axis, this is on the axis, so its distance out is 0. This is also on the axis. Its distance out is 0. So the only moment of inertia we have is this mass right here So the moment of inertia is going to be mr squared for a point mass. Remember that. So we've got 9 times 1 squared, so that's going to be 9 kilograms meters squared. So now, if instead of rotating about the x-axis, what if I rotated about the y-axis? Wink. If I rotated about the y-axis, this and this both have a radius of 0. They're on the y-axis, right? So their distance out is 0. So my moment of inertia is going to be 2.5 times 2 squared, or 10 kilograms meters squared. Now, instead of those, what if instead I said, okay, our axis is coming out, staring straight out at you, that z-axis, and we are rotating about that z-axis. Obviously, the 1.2 has a distance out of 0. So we're going to have the moment of inertia be 9 times 1 squared plus 2.5 times 2 squared. So that's going to be 19 kilograms meters squared. So we could rank these based on, from least to greatest, which one is going to have a greater resistance to spin, resistance to that rotation. Now, where we left off last class, we looked at problem 5, and we ranked that based on the orientation of the dots from those axes of rotation. And then we were looking at problem 6. So problem 6, we talked about where the center of mass was located at, and it was determined the center of mass is at point B. So at this point, try and come up with a ranking for those. Okay, I'm going to add that to Canvas, to our discussion questions, so that you guys can talk about that online.